In this video, we introduce the Linearized Double Inverted Pendulum or LDIP model and show some of its applications in humanoid push recovery. The LDIP is a simplified model that can approximately represent the dynamics of a complex, high degree of freedom humanoid robot. When humans are pushed, they try to rotate the arms or lunge their torso forward or backward to balance themselves. This generates an angular moment of inertia about the pelvis, which helps in regaining the balance. LEIP takes these things into consideration and models this angular moment of inertia implicitly. The implicit modeling of angular moment of inertia in LDIP facilitates the use of modern control techniques like linear quadratic regulator with ease. The controls implementation for this work uses an LQR to calculate the control forces required by the model to balance the robot, while a PD controller is used to calculate the force component required to counterbalance the forces due to gravity. Finally, joint torque signals are computed by relating the control forces with the joint torques using the Jacobian matrix. To evaluate the model performance, LDIP has been implemented and simulated in MATLAB. The robot is given an initial velocity at the pelvis to simulate an external impulsive disturbance that changes the velocity from state of rest to the given test case velocity. An initial velocity of 0.5 meters per second is given at the pelvis of the robot. The red arrow indicates the direction of the external impulsive disturbance. As we can see, the robot lunges its torso forward to generate the angular moment of inertia about the pelvis that helps it to recover from the push. The LDIP model is validated in Gazebo using simulation model of the RIT's humanoid robot TigerBot 7. In Gazebo, an initial velocity of 0.35 meters per second is given at the pelvis of the robot. As the external impulsive disturbance is applied, the robot successfully recovers from the push and maintains its balance. Based on the results, it can be observed that the presented control architecture achieves the task at hand with minimal effort and force requirements. This enables the robot to recover from a wider range of disturbance without the need for taking a step.